In this lesson, we are going to learn about de Broglie wavelength. Now, this is not the correct pronunciation, actually de Broglie, but we'll pronounce him as de Broglie. In 1924, French physicist Louis de Broglie, while doing his PhD, suggested that if light can have both wave and particle properties, electrons, particles like electrons, also must have wave properties. For a photon, a particle of light, E is equal to hf. Right? This you know. And what is frequency? C by lambda. So E becomes hc by lambda. Right? So what is lambda? hc by E. Right? We can take C downstairs. We get h by E by C. And what is E by C? Momentum of a photon. So lambda is h by p for a photon. So de Broglie said, if lambda is h by p for a photon, lambda must be also h by p. De Broglie said that if lambda is h by p for a photon, lambda must also be h by p for particles like electrons. So for a material particle, lambda becomes h by p again. But for a material particle like electron, what is p? Momentum. Momentum is mass into velocity. All of you know that. Momentum is also root 2 km. You know that? P is mv. What is kinetic energy? Half mv square. Right? So mv whole square by 2m. What is mv? P. So kinetic energy becomes p square by 2m. If kinetic energy is p square by 2m, what is p? Root 2 km. Right? Therefore, we can write this p as root 2 km. K is kinetic energy. M is mass. Right? This equation is valid always. Right? Not just in modern physics. In classical mechanics also you can apply K as p square by 2m and p as root 2 km. So lambda has become h by root 2 km. Suppose you take a charge q and accelerate it through a potential difference v. It will get a kinetic energy qv. So this lambda becomes h by root 2 qvm. Right? Many times we talk about de Broglie wavelength of electron. So then you put the charge of electron here, E, which is 1.6 into 10 to the power minus 19 coulomb. You can put the mass of electron here. And then we put all these constants. Then lambda in angstroms becomes root over 150 by V in volts. This is a simplified equation that you can remember to calculate the de Broglie wavelength of an electron quickly. Now experiments have been done with electrons. We show that electrons have a wave nature. People have done interference experiments with electrons, with iodine molecules, which are quite big molecules, with fullerenes, those are known as buckyballs, carbon 60, carbon 70 molecules. And these experiments show that these particles have a wave nature. In fact, electron microscope uses the wave nature of electrons. For large objects, the wave nature is not significant. People have not done interference experiment with cats, dogs, human beings. But for particles like electrons, iodine molecules, fullerenes, the wave nature can be shown, okay, people have done interference experiments with these particles. So in this lesson, we learnt about de Broglie wavelength, the wave property of matter. Louis de Broglie suggested that if light can have both wave and particle properties, electrons also must have wave properties. And for this, he used this analogy. Lambda equal to h by p. H is Planck's constant, p is momentum. That becomes h by mv for a material particle, and that is also equal to h by root 2 km, where k is kinetic energy, m is mass, and k is qv. So finally we get a formula h by root 2 qvm. Now for an electron, the equation simplifies. We put all the constants. Lambda in angstrom is equal to root over 150 by V in volts. This is about de Broglie wavelength.